I noticed while I was creating videos that the automatic subtitles which were being generated in TikTok were way better than the ones being generated in Instagram, and I wanted to know why. Word on the street is that TikTok is shutting down in the US. I became really interested in automatic subtitling. The ones in Instagram were pretty awful, like not even close to correct, completely unusable. And then later, I actually realized that the reason why this was happening is that I had the configuration settings in both applications set to Spanish. And so in Instagram, what was happening was that the app was anticipating that I would be speaking in Spanish. But since I was actually speaking in English, the subtitles were like coming out crazy because I guess the app under the hood was using a single language audio to text transcription model. And in Instagram, when you're generating the captions, it doesn't give you an option to actually change in the UI to change the language that it bases the transcription on. So this means that if you're a multilingual speaker like me, anytime you want to record a video in the other language, you actually need to go into the app's global settings and change them, which hard resets the app and you have to completely restart it. So in comparison, when you're in TikTok and you're generating subtitles, it actually shows you an option in the UI to change the language, which I think is a really nice feature. So in general, I do think that TikTok is a little bit friendlier UI to multilingual speakers, which I guess makes sense since it's a Chinese app being used by English speakers, I think primarily. Someone can fact check me in the comments, but I heard that people in China don't even use TikTok. I don't know if that's true. I just heard that just the other day. Anyway, I'm willing to bet that this is, probably was this small feature was a very conscious product decision, and I think it was a good one in TikTok. And this whole process kind of sent me down the rabbit hole of wondering, why it might be preferable to use single language models for audio to text transcription rather than some kind of larger general purpose model which can do multi-language. So all of the answers to the previous questions I sort of talked about are explored at length in the Google white paper, Scaling Automatic Speech Recognition Beyond 100 Languages. And even though really some of the most groundbreaking stuff in the paper is all about how the team built this model which scales out to more than 100 languages, many of those languages of which are low in training resources, meaning that maybe there's not a lot of YouTube videos out there of that particular language, for example. There's still a ton of interesting and useful information about how audio signals can be used once they're converted into numerical vector representations. And the authors of the paper talk about the development of this USM, the Universal Speech Model, which uses a 3-stage training pipeline. So first there's unsupervised pre-training, which is where the model's encoder is trained on a huge unlabeled multilingual data set. So in this case, it's mostly YouTube videos. And by unlabeled, we just mean that we have only the raw audio from the videos, no text script alongside the audio. Next, there is multi-objective supervised pre-training, which uses a variety of different techniques using both unlabeled and labeled data. And labeled data in this case is the same sort of YouTube videos of, we extract the audio from the videos, but then you also have verified text scripts for the audio alongside it. And then finally, there is supervised fine-tuning, which is task-specific training for downstream applications. I'll talk more about that later. A big technical innovation here is the introduction of chunk-wise attention, which helps with processing really long audio samples. So traditionally, an attention mechanism would degrade rapidly with long audio sequences because it's a ton of information to keep in context. And you would imagine that maybe for a 1-second audio clip, it gets converted into this vector representation of, I don't know, it represents the waveforms. Maybe it's hundreds of numbers for just 1 second of audio. I'm not exactly sure, it's sort of an arbitrary example, but you get what I'm saying. You run up against compute constraints. What the researchers in this paper found was that they could get better results if they chunk the audio into 8-second groupings. And when you do chunking with attention mechanisms, typically you might run up against what's called a boundary problem, where there could be accuracy issues at the edges of the chunk boundaries because there's less context available on one side or the other. So you could imagine, imagine this is a vector representation of, let's say, a 30-second audio clip. And this is actually like hundreds of thousands of numbers in this vector representation. Up against the edge of this chunk where the attention mechanism is, it only has sort of one side of the boundary to take in, that's looking at a time. That's what we're talking about here. So for example, if the chunk we're examining contains the audio, it was as if he went, and it cuts off there. There might be some missing context that could help inform whether the word went is being used literally, like in he went to the beach, or as a euphemism, like in he went crazy. And the authors of the paper actually never mention any degradation of quality after chunking. So from what I can tell, this doesn't seem to have had any measurable negative effect on the outcome. So the USM model achieves several notable results. There's great performance on multilingual ASR and speech-to-text translation tasks. ASR here being automatic speech recognition. There's better performance than OpenAI's Whisper, while using only 1/7 of the quantity of labeled training data, and effective adaptation to new languages with minimal supervised data. And one of the really interesting points here that the authors is that the authors were able to get really efficient results on many languages by deploying a single full-size multilingual model, but fine-tuning the model with residual adapters for specific languages. And this ends up only adding 2% additional parameters to this already large single model, in comparison to, say, deploying a single large model for every language. So in summary, diverse unlabeled data is more practical for building usable ASR for low resource languages than weakly labeled data, though domain relevant labeled data is still optimal for maximizing performance in specific applications, and I'll talk more about that later. It's super cool stuff. So the paper goes much more in depth on things like efficient transformer architectures for specific downstream tasks and attention and language specific adaptation mechanisms, and I'll leave it up to you, the listener/watcher, to go check that paper out if it piques your interest. So interestingly, every time I'm like, I start. So interestingly, this project was actually born out of kind of an accident. Like I mentioned earlier, the reason why I became interested in figuring out how to automatically transcribe videos was kind of due to a mistake. When I didn't realize that my application-wide language settings in Instagram were actually affecting the quality of the audio to text transcription. And then later, when I set the global language to English, the automatic transcriptions suddenly started doing a really great job of creating accurate subtitles. Go figure. That was the secret sauce, and I kind of just made a silly mistake. Although arguably, in the UI of Instagram, it wasn't obvious at the time. Maybe a feature, not necessarily a bug, just maybe something that the product team hadn't thought through. I don't know. Anyways, I got curious about the whole process, so I built my own Subtitler pipeline. High level, I wanted to be able to record a video on my phone and then drop it into Dropbox or some functional equivalent app on my phone, and then I should automatically get back out the same video, but just with the subtitles added. So at first I was thinking, all right, simple enough. I already use Dropbox on my phone. I'll just drop stuff into there, and then I'll have some kind of listener hook into the Dropbox directory and ping like a Lambda function in AWS when something changes. Now, I had already this year been through the ringer in a similar project working with SharePoint and Azure functions, and I know from experience that there's a really good chance that with a third-party storage system like Dropbox, I might not be able to get a clean notification into a Lambda function. Basically, what I found out with SharePoint pipelines is that the only way you can do this is to hook into the SharePoint API for subscriptions, create a new subscription, and then have that subscription ping Azure when something changes. But that ping about when something changes in your directory doesn't actually give you the full details about what changed, just that something in that directory changed. So when Azure gets the ping that something changed, it needs to go back into the SharePoint directory and look through the files to figure out which files have a newer timestamp than the last sync and retrieve their contents. And this whole back and forth messaging restriction is a huge pain in the ass, and I wanted to avoid that if possible with my own Subtitler pipeline in AWS. So I figured instead of Dropbox, where we'll probably run into a similar restriction as SharePoint, it would be most likely much better to just dump the file straight into S3, because I know that we can just use S3 notifications to directly pick up on the changes. I've done that sort of thing before. I know that with this pipeline, you don't need to do this like weird back and forth. You just get the information about the file that changed directly in the S3 notification. So when you upload a video to the upload bucket in S3, which by the way you can do directly on mobile because there's a mobile S3 client app, this triggers the Lambda function via an S3 event notification. The Lambda function downloads the video file to temporary storage, and then when the file is in temporary storage, we use FFmpeg to extract the audio layer as a 16 kilohertz mono track wave file. So why these particular settings? In case anyone is interested, in the white paper I mentioned earlier, it seems like 16 kilohertz is the industry standard for working with spoken word. They even mentioned that all of the audio samples they worked with were normalized to 16 kilohertz because it seems to be sort of like a sweet spot where if you upsample a lower quality track, there are some audio artifacts introduced, but not enough to actually matter in isolating spoken word. And if you downsample a higher quality track, 16 still gives you enough data to like clearly pick out the nuances of spoken word. And as for the wave format, wave is uncompressed, which means you get, again, less noise artifacts, better transcription accuracy, and mono. Mono just means, we're working essentially with a single track as opposed to stereo, which is when you're listening to music and you hear different things in each ear. Stereo is great for music listening, but mono is fine for spoken word and makes the track less complex to process. So why FFmpeg? It's pretty much industry standard for audio stuff, especially spoken word in particular. Although if you're interested, there are some other products out there like Remotion that are trying to sort of disrupt this space. It's a pretty cool project. You should go check it out. FFmpeg is fast. It's simple to use with Python. I've used it before with music stuff, so I'm familiar with it. It's been battle tested for a long time. I'm using it in my project both for audio extraction and actually burning the subtitles onto the new video. So the WAV file that gets extracted is automatically placed into an audio directory in the upload bucket. Then the Lambda function takes the audio file and starts the transcription process using AWS Transcribe. So every time this process fires, it creates a unique job. That unique job gets a unique job name containing a timestamp and a UUID. And this is basically just to avoid an error I was hitting in Lambda, where if you try to process if you try to run a single process multiple times with the same job name, it'll fail. To be honest, I didn't really look like too heavy into best practices around this. I just wanted to kind of skirt around that issue by automatically making sure each process was unique. That seems probably good enough for now. Again, like somebody fact check me in the comments if that seems bad. I don't know. So the Lambda waits for the transcription process to complete, which is usually done in a matter of milliseconds to seconds, depending on the size of the originally uploaded video. It's pretty fast, and the nice thing about AWS Transcribe is that in addition to the speech to text, it also provides timing information, which we need later on for the subtitles. So to actually work with the timing information, you need something called an SRT file. SRT is basically, it's just a particular way of formatting text for captions and timestamps, and a lot of different programs use, for example, if you've ever used Premiere or any other Final Cut or any other professional video editing software, you know that there's an option, if you want to add subtitles, there's an option to import your own SRT files. And since AWS Transcribe doesn't directly generate SRT, we have to take the JSON that it does provide us and convert it. And this is all possible because the outputted JSON has keys like start time and end time and pronunciation and things like that we can use to make heads or tails of what the data that we actually want to extract is. And from there, like I mentioned earlier, we use FFmpeg again to burn, burn the new subtitles directly onto the new video. We call this burning, like how we used to burn music onto CDs, because the text actually becomes a part of the new video artifact itself, rather than like an overlay like you might see on YouTube. And then the final video with burned subtitles gets uploaded to a different S3 bucket for processed videos, and we can download it again to our mobile client from there. So the whole process is serverless, which is nice. As of the time that I'm recording this video, I've run this process probably about 50 times, give or take, videos of differing lengths, anything from about 5 seconds to 30 seconds, and my forecasted cost for the month is only 13 cents. So the average cost per video transcription is under, video transcription under 30 seconds is usually less than 1 cent. So really kind of the one black box in this system is AWS Transcribe. So I'm curious what AWS Transcribe actually uses under the hood. I've done some light digging, and I can't really find anything explicitly disclosed about what model or models they're using under the hood, or how the audio gets filtered or anything like that. But based on the paper I mentioned earlier, we can probably take a pretty good guess and say they're probably using a similar architecture to the other ASR, again, automatic speech recognition systems. Most of these systems use what's called a sequence-to-sequence model architecture, which basically just means that we are converting from one type of sequence to another. So that could be numerical, text, characters, binary or booleans, so from one of those formats to another. And in this case, the input sequence that we're converting from is a list of numbers, a vector of numbers representing sound waves over time. And the output sequence is a list of text, and this text is actually the spoken words, the actual words which were spoken. And one of the interesting things about this process is that the input and output sequences can be completely different lengths. So for example, a 3-second audio clip represented by a fixed list of numbers, fixed list maybe for 3 seconds, I don't know, again, I don't know the exact numbers, but maybe let's say it's 1,000 numbers representing 3 seconds of audio. That could become a new sequence of 5 words, or it could, if the speaker is speaking really fast, it could become 15 words. So there's kind of some variability in there that has to be accounted for. So the model architecture uses basically 3 components. There's an encoder, which processes the audio features into the list sequence of numbers representing the waveforms. Then there's a decoder, which converts the numbers into text. And then there's also an attention mechanism, which helps to align the audio and text as accurately as possible. And when we're talking about attention in the context of audio transcription, again, we just mean that once the audio is transformed into a vector data of numbers representing the waveforms, the attention mechanism is doing this kind of like sliding window effect, where it's figuring out which numbers are contextually relevant to group together to form words or phrases. Also, like what we saw in the paper, there's probably a massive set of training data, like sources like YouTube, some labeled data, probably mostly unlabeled data, all different languages, and a huge variety of stuff like different discussion topics, speakers with different accents, different background noise, the list goes on. And we saw in the paper also single language models almost always outperform multi-language models, but there are certain scenarios that multi-language models need to handle, like scenarios where there is actually mixed language in the video itself, either via the speaker or speakers changing languages, or changing dialects. So it would be interesting to know exactly how AWS is handling this under the hood, like whether they're using that same method of having a large single multi-language base model and then just including different single language adapters where needed. If anybody is watching this and works on this, definitely chime in. If it's not in your NDA or something, be very curious to know. One quick addendum, something also cool worth mentioning about AWS Transcribe is that when you're using it, you don't have to use the default language model. You can actually use custom language models which you train yourself inside of the platform. And the explanation given in the AWS documentation is that you may at certain times need certain vocabulary or grammatical, structural understanding or code switching that differs from the norm. of any particular language. For example, if you're transcribing something which uses highly technical language, you might want a model that is fine-tuned for that particular domain. This is one of the problems that I've often run up against while making software engineering content for TikTok and Instagram. There have been a lot of instances where, I might say something, I'm talking about data structures and I'm talking about queues and stacks and things, and the automatic audio transcription spits out the letter Q rather than the full word Q. In this scenario, you may want a model which is fine-tuned on software engineering discourse so that it can pick up on the surrounding context and actually, know that you're talking about the Q data structure rather than the letter Q. This could be particularly helpful in my scenario since, I'm just automatically burning the generated subtitles onto the new video. There isn't, any review process in the loop to make sure that the generated subtitles are actually accurate. I'll talk more about this in just a minute. By the way, if you have a large enough training corpus, training material, labeled and unlabeled data, the best thing to do in this case would probably just be to fine-tune a model on your own content. Personally, I think this is probably like huge overkill, but it's sort of an interesting thought experiment in pros and cons of your time versus the effort versus how good the results are, etc. By the way, I'm also using the term fine-tuned here kind of loosely. When we create a custom language model here, it might actually be more useful to use something like the term coarsely tuned. There is a dedicated API inside of AWS Transcribe which lets you create new language models, and as parameters you can pass in additional text files as training data. Both actually what they call both training and tuning data, and I'll link the documentation below if you want to read more about that. Of course, in a really robust audio to text model, text data is just one component. There doesn't seem to be any way to actually input your own audio data, whether it's labeled or unlabeled, for further training. And here's an interesting side note on whether or not you might even want to include some sort of review process for the subtitles somewhere in the loop to make sure that they're correct. You might not. Here's a counterpoint to why you actually might want your subtitles to be slightly off. So if you've been around the internet for a while, you know that a good deal of content out there is engagement bait. And some of it is really egregious, like total clickbait slop. That's not really the stuff I want to make. Sure, it can make a lot of money, but it doesn't make me feel good. I genuinely want to help people learn via the technical videos that I make. And I do think there's a sort of interesting middle ground here. It's possible to take a little bit of what we can observe from looking at how engagement bait works and apply it to actually useful content. For example, of course I don't really have any like hard data on this, it's purely anecdotal, but what I've noticed on my videos is that sometimes if the subtitles are wrong at certain points, that gets people to comment. For example, if you say computer, but the subtitle says poop her, that gets more people to comment. And when more people comment, your video gets shown to more people. And so in theory, if a video is genuinely useful or insightful, the more people it reaches, the better. Now, there's definitely a counterpoint you could make, like, well, maybe the people who make those types of comments, the algorithm shows your videos to the wrong audience, and then, it's sort of this negative feedback loop. That may possibly be true. I'm not really, thinking about it that deeply. It's just sort of an observation about what people engage with. So future plans for my Subtitler project. Right now, the subtitles aren't actually getting, burned onto the video correctly. I still have to figure out how to get each individual text section from the SRT file to burn onto the new video as individual subtitles, because right now it's just getting burned on as one giant block of text. So that's something to figure out. There's also some visible video quality degradation, which I'm not sure whether it's a function of something to do with FFmpeg or something to do with the AWS pipeline. I got to figure that out. And then of course there'll be the matter of some styling to make the subtitles actually look pretty. So that's where I'm at for now. More soon. Reading the white paper stuff about audio was interesting, especially because pure language stuff is really at the forefront. Pure language, text and language stuff is at the forefront of what everybody's talking about in machine learning circles right now. But this audio stuff is sort of an interesting side quest anyway. Thanks for watching.